An LED filament lamp. Those of you who watch Julian Eyelet may actually recognise the sort of layout of the filaments, this sort of conical shape with strange supports. Each filament has a support that has a connection at the base and a connection going up to the top, but they both sort of clip into the circuit board. And Julian was going to use his in his outdoor 12-volt system, but I don't have an outdoor 12-volt system, so I am going to open mine. But let's try it first. So with 12 volts, and the polarity doesn't matter, it's non-polarity sensitive. At 12 volts, it draws approximately 450 milliamps. So this thing is rated 6 watts, that's close enough. Interestingly, if I then turn the voltage down, let's turn it down to the point it starts dipping. Okay, it starts to dip round about there, which is 4 volts. So if I turn that up to, let's say, 5 volts, it's drawing about 1.7 amps. Let's watch that working out as power-wise. 5 volts times 1.7 amps equals... Oh, it's gone up to about 8.5 watts. I wonder how much of that is losses in the power supply versus the actual, the LEDs themselves. Interesting. It does suggest that you could use this lamp in a USB power supply. Now, the top is plastic, so I don't stand too much of a risk of injury if I do this. That is a very odd structure. Oh, they're quite springy as well. That almost gives it resilience against being dropped or bumped about. That's quite intriguing. It appears to be staked in, or is it... hold on, let's get a screwdriver and prise it out. They've heat staked it to actually jam it in position. So here's the circuit board. Oh, right. I'm wondering, is that... are these parallel arrays of LEDs? We can test that. Here's the circuit board at the bottom. It's hot melt... I say it's hot melt glued. I think it's silicon goopy glued in. Oh, it's a tiny little power supply. This is clearly designed to go into the base of something like a GU10 lamp. It's got the inductor, it's got a capacitor, it's got a diode, and there'll be a little chip in the back. Oh, there's a full bridge rectifier in the back. And then there'll be the switching regulator, the sort of buck regulator. Okay, that's quite interesting. It's unfortunately, goo has covered the chip itself. Let's try and get some of that goo out the way. And see if we can read the number on the chip. I may not be able to read the number on the chip at the moment. That's okay. If I can't read the number on the chip now, I'll pause and I'll find the number, because there definitely is a number. It doesn't look terribly clear. I'm going to have a go with the little magnifying glass. Oh, it's XL Semi. XL Semi, and the silicon goo, XL, I think it's 6061E. The silicon goo has actually gone in and it's laser etched, and it's kind of, I don't know if you can see this. Let's try a bigger lens. I don't know if you can see that, but you can see part of the number, but not the whole number. It might be that you can see it easier, better than me if you've got a big screen, because you may have more detail. That's the peril of high definition. You actually get better vision than me. Yes, better picture. That is kind of cleared off a bit, but it's still not cleared off that well. I shall explore that later. In the meantime, let's just chop this off and get the bench power supply on again. And we'll just strip these little gooey silicon leads. The very soft, flexible, silicony stuff. And let's see what voltage the LED array runs at. I reckon it's a parallel array. I reckon that as soon as I go above about 2.5 volts, and I could be wrong here, they should start lighting. I might be completely barking up the wrong tree. It might actually boost the voltage. So let's set the power supply. Let's bring in the meter. Actually, let's bring in the wee dinky meter, because it's got the alligator clips on it. A nice contrast from the fluke. So I'm guessing this is negative. I'm guessing this is positive. Let's bring in the power supply, which is set quite low. And we'll stick that on there. And we'll stick that on there. And the voltage at the moment is... Why am I getting a negative voltage there? What have I done here? Wow, that's impressive. Oh, there we go. Right, let's turn this up. Let's zoom down a little bit. This is the curse when I zoom down, because then, you know, I'm going to screw up and I'm going to forget I'm zoomed in. We're currently at 0.9 of a volt. I would reckon that if these are all in parallel, then they're going to start conducting. There is something grossly wrong here, because I am not getting the correct reading from this meter. Is its battery flat or something? Is this just a terrible advert for these shitty meters? What on earth is going on there? Wow. Oh, there we go. That's unimpressive. Right, it's the dial, the rotary dial. That's exciting. It just goes to show you that spending an extra £1 does make a difference. The voltage is creeping up. I'm not getting any light from those LEDs yet. I would have thought they'd have been lit if they're in parallel, unless the polarity is the other way around. Negative is shown, negative and positive. So let's keep pumping the voltage up then. Maybe that is a little boost circuit. The voltage is rising. The voltage is rising higher and higher and higher, and still nothing's lit up, and suddenly I'm full of doubt. That's quite a high voltage. Right, okay. As a precaution, before I go any further, I'm going to swap the polarity in that in case everything is marked wrong, because you just never know. Let's put positive on that. I suppose another clue might be to look at the capacitor rating in the power supply, the output capacitor rating, and see if it's rated quite high or not. 25 volts. It's not that high. Let's make a half-assed attempt at gripping this cable. And we'll start again. So, voltage going up. I would have expected them to be lit at that if it's right. Okay, so it's not a parallel array of LEDs at all. I reckon that, are these all connected in series? They might be. Hold on, let's get the daddy meter in. This is probably a better idea. Let's zoom back out again so you don't miss any of this. Let's do some continuity checks with the daddy meter, the domometer. So this one is connecting to there, but not to there, and that's connecting. These 6 filaments may be in parallel, but right, okay, let's see if I can make this glow. I'm going to have to take this off camera momentarily. Yeah, it's glowing. I don't know if you're going to see this. The meter is making it glow. Those are roughly 3 volt filaments each, and it looks like there may be 6 in series. Right, let's start the experiment again. So now let's get the meter back here. Stick it in positive, because I think that is the correct polarity. And the negative. And this time we're going to go for gold. I'm going to change the range in the meter. Let's do that while the power is off, shall we? Turn it on. Okay, so we've got about 3 volts at the moment. Let's zoom back down on this. And wind the voltage up optimistically until I see a current deflection happening here. So there's 6 times 2.5. Hold on, let's see what voltage should I be expecting here. 6 times 2.5, so I don't get overzealous, equals, I reckon at 15 volts, which is very close, it's going to start glowing. Oh, can I screw this video up anymore? Can I do more wrong with this video? Right. What the heck's going on here then? Let's get that down a bit. Is the polarity correct? Hold on. Zoom back out again. Yeah, I'm screwing everything up here. This is sometimes what happens. Nothing ever actually happens as you're expecting it. Let's just out of interest, let's do a quick polarity check here in the meter. So let's put this to continuity. I'm just off shot here. I'm just double checking that. Okay. Oh, that is not going to show. That's a completely... Everything's going wrong. That's just what happens sometimes. That was the wrong type LED I tried testing. Right, okay. I've validated that positive should activate the... Should be positive for the LED. So let's go on to here. And again, it's so bright here. I'm going to have to come off shot momentarily. Just bear with me a moment. That does appear to be the correct polarity. What on earth is going on here? Did I have a bad connection before? Let's try that again. This is all gone horribly wrong, and because I've now stripped the lamp to bits, I can't actually stop the video. I'm just going to have to plow on in what is turning into an absolute apocalypse. It's the video where everything went wrong. Sometimes that happens. Best laid, best made plans of mice and men. And it all goes pear-shaped. The final piece of icing on the cake would be to connect it up to the supply here and just blow up all the LEDs accidentally. So 10 volts. I'm going to crank the voltage up higher. I thought they were doing lighting by now. That's odd. All right, okay. I think rather than make a dick of myself anymore, I think I'll just pause momentarily and then work out what's happening here. And just like that, all the problems are resolved. And as Eric O at South Main Auto might say, there's your problem, lady. Two of the filaments in my bear-like force that I used to get this cover off actually snapped these tops off the filaments where the connections go in the top, so they're quite fragile that way. Just be aware of this if you ever want to open one of your own lamps. It can break them. If you do, you have to just flex top slightly to see and it will part, and then shut them out with solder underneath. So we're back. And I also took the opportunity to find the datasheet, which is the XL6001, and is, to quote, a wide 3.6 to 24 volt input, constant current sense driver for driving between 3 to 8 series 1 watt LEDs, and that makes sense. It's got a fixed 400 kilohertz switching frequency, and it's effectively treating each of these filaments. These are parallel. It's treating them as a single LED, but it's actually a parallel array, and the placement of the LEDs in them is very random. I don't know if you can see that, but if we zoom down in that, how far can I zoom down before it goes a bit weird? You'll see that the spacing in them is a bit sort of, it looks like a barcode. It's a bit strange. But it's treating each of them as a 1 watt LED and wiring them all in series, and then runs them at a current that's programmable by a resistor. So I'm going to ramp this up now, as you can see that the voltage across it is typical of, it's just gone to current limiting at 11.3 volts at 300 milliamps to set the current limit to. So that is, just treating them as a 1 watt LED, running them about 350 milliamps or so. That's quite interesting. Let's turn that off. Let's turn the soldering off so it doesn't make loud buzzing noises in the background. And let's take a look at the circuit here that is very clearly the sort of power supply you'd find in the base of a sort of MR16E type lamp. I probably said GU10 out of habit earlier on. Yeah, MR16E type lamp, which will drive an array of, well, it can drive from a 3 watt to the 8 watts of a array of LEDs. The schematic, we don't have to worry too much about the block diagram here. It's a very simple chip. Well, I say it's very simple. All the work has been done by XL Semi. The supply comes in. It actually has a rectifier before this. It's got a couple of smoothing capacitors. It powers the chip at pin 2, and it's also got a reference in 7 and 8 to ground. The reason it's got 2 pins for the current switching and the connection to ground is just to actually share the current between them. It's got the inductor. In that case, this chunky little inductor here, what's it rated? 470 microhenry? Or is that 47 microhenry? Don't have something to test that. 470. Let's just presume that it might actually just be a 3-digit code, so it would be 47 microhenry, which kind of makes sense. It does show a 22 microhenry here. That makes more sense. It's got the diode, which is next to the inductor here. And then the output capacitor, and that's fundamentally it. What it's doing here is it's pulsing this inductor to build up a magnetic field in it, and then when it turns off, that field collapses and it sort of adds to the input voltage and goes through that diode and boosts the voltage up to drive the LED. The LED has a current sense resistor. Where is that? Where's the current sense resistor? I would expect to be near the output. Could it be these resistors here? One moment while I just magnify. 0.9 ohm and 1 ohm, 10 ohm. That would be quite accurate if it was a... Is that right? Let's scrub those. It's a bit... it's got more goop on it. Yeah, it looks like a 10 ohm. Let's show you that. And then lower value. So I'm guessing they might just be fine-tuning the value there to get what they want. And the idea is that when the voltage exceeds a certain threshold across this resistor, this sense resistor, it then starts cutting back and regulating the current a bit, so that way it can actually sense current flowing through the LEDs. It's an interesting variation. I've never seen this particular structure, this mounting arrangement of the filaments before, where they're a parallel array on a ceramic base with a hole through for that to solder through. They've got a layer of the phosphor in the back as well, so any of the blue light creeping through from the LEDs through to the back through the ceramic layer does also contribute the sort of warm white light as opposed to the cold white or that it would create if it was just the bare blue on its own. But most of the light will come out one side, and you can actually see a slight ripple on the gel here where it's got the LED chips underneath it. It's an interesting structure. It's quite neat. It's an interesting way of driving them, just treating each as a 1 watt LED and wiring them all in series. That takes me by surprise because I really thought they were all in parallel, as you saw at the beginning of the video, which dragged for me, by the way, because everything was going wrong. That's what happens when videos go wrong. It's almost like time stands still. Actually, it's not like time standing still. It's like it just seems like it's taken ages. Every screw up actually seems like it took minutes. I'm not sure how long it did take. I'll find out and look at the video. But there we go. That's what's inside these lamps. Don't take them to bits. They're very, very fragile. But you could theoretically just scavenge. If you can pop one open carefully, you can then scavenge the filaments out. I guess you could carefully desolder these wire supports from them and just put a couple of wires in if you wanted, or create your own sort of frame. And they are just effectively a 3-volt filament, each of them. Up to about 350 milliamps, so quite neat. Useful as a source just for those filaments. Oh, this video has just redeemed itself in a very interesting way because I took a closer look at one of the filaments. I cut a new one off, and initially I got one of the broken ones and I scraped the phosphor off, and I was thinking it would be lots of little chips with bond wires onto them, and it's not. So I actually, in scraping the phosphor off, all the LEDs came off too and left no sign other than little bus bars with solder on them. So I took another one and carefully picked away the phosphor-loaded gel around one of the LEDs. And here's the construction. So we've got ceramic. And now how many LEDs do we have in here? We've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, about 22 LEDs in there. And each LED is mounted onto a little bus bar down the middle. So if this is the ceramic strip, we've got two little sort of silver coloured bus bars coming down the full length with all the LEDs in parallel. And everywhere an LED is mounted on it, there's this really neat little perfect package that lights even blue. I've powered it up and looked at it through the microscope at low level. And it's physically just soldered. There's no bond wires, no jumping wires anywhere. It's just physically soldered straight across those bus bars. So whatever machine has placed them is just basically soldering like tiny little LEDs along that bus bar. Lots and lots of them, with a rough spacing to give you an idea of size here. Glasses off. I have to take the glasses off to get the microscope down, and then hold on, just give me a second here, bear with me. Oh blimey, it's really wide space compared to the LEDs. Rightio. So it's equivalent to about that spacing. That's the size they are. So if you imagine that, this strip is about the 22 LEDs along it, this is the sort of spacing you can imagine what size they are. And as I say, I was kind of expecting it to have those, like a chip, a pad with a chip, and then a bond wire jumping across, and then another bond wire going on top. And this is just so streamlined for mass production. This must be also how they're probably making the large cob arrays as well. That is a very interesting evolution. Strange. I wonder why that when you look at the LED, if I drew it a bit bigger, it's got these sort of electrode dots like that, and then a couple at the other end as well. And from this one, there's a little stripe which is presumably a surface electrode, and these ones too. So I wonder if these are like just connecting through from, oh, there's a thing. That's probably what it is. These ones will be connecting through to one substrate. Is that right? No, how would it then connect? No, I'm absolutely talking crap. No, I was trying to work out how it connects from the bus bar down below up to that, but without actually going in like super microscope stuff and really sort of reverse engineering it with like lab grade equipment. I'm not sure how you could actually determine that, but I'm guessing that these bare dots in their own will be one layer, and then these will be in the surface. These are the other layer to actually spread the current over the surface for even illumination. That's very interesting. It's a new twist in the sort of cob chip on board type array LEDs that I've just never seen before. That's very interesting.